Good morning, everyone. Thanks for your coming. I'm Yingwei Pan from University of Science and Technology of China. It's my great pleasure to present and share our work today. Actually, it's a collaborative work with my mentors, Dr. Meitao Yaoting and Rui Yong from SIA, and my supervisor, Professor Li Houqiang from USTC. And our main task today is video to sentence, which can automatically generate a sentence for the given video, just like the 3 short videos. And the research on video to sentence has proceeded along 2 dimensions. The first is the language template-based model, which firstly predicts the words for describing the subject, verb, and object, which might be the key concepts in the sentence. For example, for this given video, this model can predict the subject as a man and the verb as a play and object and is a guitar. And then, by utilizing the language templates, it can easily generate a sentence like a man is playing a guitar, which is simple and in a fixed form. So for this kind of model, we can see it mainly focuses on the relevance between some key concepts in the sentence and the video content. And another direction is a recurrent neural network-based model, which is quite similar to that of image-to-sentence tasks. Both of the two works are based on the RN, which is the training techniques to solve the sequence-to-sequence problem. So, especially for the video-to-sentence task, it's aimed to decode the video representation into the sequence of the words, which is the description here. So, giving a video first, we can use the 2D CN to extract the frame level representation, and then OptiFlow or 3D CN also can utilize to represent the temporal information. And then the video representation is generated by pulling overall the frame level and click level features, which will be injected into the RN model later. So the RN model here is to predict each word in the sentence, giving the video content and all the preceding words. It should be noted that the video representation can be injected at the first time step or at each time step. And for this RN-based model, it mainly focuses on the contextual relationship between the word in the sentence, which can be seen as such kind of coherence among the sentence. So, from the 2 kinds of models for video to sentence, we can get to 2 key issues in this task. The first is the relevance, which represents the relationship between the semantics of the entire sentence and the video content. And another key issue is the coherence, which can make the sentence logically and grammar correct. However, the existing RN-based model are mainly focused on the coherence, while leaving the relationship between the sentence and the video content unexplored. For example, given this video, the LSTM, which is one kind of RN, can generate a sentence like a man is playing a guitar, which seems logically correct, but the semantics of the sentence is not relevant with the video content. So in our work, we aim to jointly model the relevance and the coherence in one framework, and to holistically looking at both the entire sentence and the video content. Okay, specifically, we present the LSTM with Visual Semantic Embedding Model, simply named as LSTME, as shown in this figure. First, giving a video, 2D and 3D CN are utilized to extract the feature representations, and then the final features is generated by mean pooling over all the frame level and click level features. Here, LSTM for sentence generation and a visual semantic embedding to measure the relationship between the sentence and the video content are jointly optimized in this whole framework. The spirit of our LSTME is to generate the sentence from the viewpoint of mutual reinforcement between the relevance and the coherence. Here, the coherence represents the contextual relationship between the words in the sentence, and which is optimized in the LSTM part. And the relevance represents the relationship between the whole sentence and the video content, which is measured in the visual semantic embedding part. So the overall loss is comprised of two components. The first is the coherence loss in the LTM part, and the second loss is the relevance loss calculated in the visual semantic embedding space. Okay, this is our whole framework, and in the experiment, we mainly conduct experiments on the YouTube to test dataset, which includes around 2,000 YouTube clips. Here, we give the two example videos with 5 sentences for each one. In addition to that dataset, we also conduct our experiments on 2 large-scale movie description datasets, which include around the 49,000 and the 68,000 movie clips. Each movie clip is annotated with 1 sentence directly selected from the movie scripts. So this is the 3 datasets we used in our experiment, and we compare our STME method with many state-of-the-art methods on the video to sentence tasks. Here, we will first show the results on the subject-verb-object triplet prediction tasks, which will evaluate the accuracy of the subject, verb, and object in the generated sentence. So look at this performance table. The first 4 methods are mainly optimized to find the best SVO, which can be seen as the item-driven model, and at last the LTM and our proposed LTME are both the iron-based model, which can be seen in the sentence-driven model. So for across the performance, we can say our method can outperform others, and specifically by jointly exploring the coherence and the relevance, our model can lead to a performance boost than LTM, who only focus on the coherence here. And in another task, the sentence generation, we choose the 3 tables which are all the performance on 3 different datasets. So across the here we also use the blue and the meter to as our main matrix. Across the 3 tables, we can see our proposed LCME can also consistently outperform other baselines. And specifically on the YouTube to test dataset, we can see by additionally incorporating the relationship between the sentence and the video content, our STME can outperform our LTM with the same representation extracted by AlexNet. And moreover, we also compare our STME with different feature representation. For example, with the deeper and more powerful features, the VGG-based STME can outperform the AlexNet-based STME, and by additionally exploring the temporal information, the C3D-based LTME also outperforms the VGG-based LTME. So finally, we find the optimal solutions to combine the different features, that is, incorporating the spatial information extracted by VGG and the temporal dynamics extracted by C3D, and use that combination of 2 features, our model can achieve the state-of-the-art performance. So this is our performance comparison on 2 main tasks. And here, this slide shows some few sentence examples generated by our STME and the baseline LTM. So it can easily find that both of the sentences are logically correct, but ours are more precise to describe the video content. In addition to that, we also show a real-world video-to-sentence demo which trained our LTME model both on the image and the video caption benchmarks. And the sentence generation result is on the left top corner, and we can see most of the generated sentences are relevant and logic correct. So, at last, as end of our talk, I want to introduce our newly released large-scale video description dataset, which is named as MSR-VGT, which includes around 10,000 YouTube clips. And for each clip, there are 20 sentences is human-generated. And we also host video-to-language challenges. And welcome to try our dataset and join our video-to-language challenges. So thanks.